professors, maybe a little bit. But at the end of the day, they were just saying, yeah, that's very nice. I like that.
Okay. We've had some technical difficulties, so thanks for bearing with us through that. Our first presenter is Derek Chou. He is a second-year master's student at the University of Illinois, Urbana-Champaign, and he's hoping to continue on to the PhD program next year. He did his undergraduate work at UC Berkeley and attained a Bachelor's of Science in Electrical Engineering and Computer Science, with a minor in Mechanical Engineering. His research interests currently include work on high-power density power converters through the use of Flying-Capacitor multi-level converters. When things are not on fire in the lab, he likes to build things mechanical, electrical, or both. Take it away, Derek.
Thanks, everybody, for showing up. I'm going to be talking about essentially flexible PCB power converters here. Now it's got to let me be able to hit this. That work? Click. All right. Here's my outline. I'll motivate the topic a little bit. We'll talk a little bit about Flying-Capacitor multi-level converters and some flexible PCBs. Then we'll go into some design and then some results. So why do we want to do this? We want to make some high power density converters that can perhaps be on some curved surfaces, like a wind turbine. Imagining, say, if you wanted to de-ice the tip of a wind turbine, you would want a high power density, something that conforms to the surface of the wind turbine. Another possible implementation would be on, say, like a motor, as a curved surface on the motor. You want to make sure that you have a very compact but also mechanically compliant kind of device that will provide your drive. And in some aerospace applications, say that you have some thermal constraints. If your power converter heats up, then maybe your board will not be in good shape if it's rigid. So a flexible PCB would just take that thermal expansion and contraction and deal with that. And our research goals in this case, high power density, high efficiency, and lightweight. So our goal is to combine a high power density power converter with a flexible PCB substrate to achieve exactly that. To get an overview of flexible PCBs, so this is a flexible PCB here. You use a polyimide substrate, and you can put some copper layers just like a regular PCB, except now you have a thinner, compliant material. You've got voltage resistance on the polyimide material, and you can design it so that it's thermal cycling resistance. You can flex it in any way you feel like. Now, to get our high power density aspect, we use a Flying-Capacitor multi-level converter. A lot of people in Pallav group have seen this before, but I'll go over it quickly. You can see that you have a high ripple frequency because you have multiple switches. So in the regular power converter, you have maybe 2 switches, maybe 3, 4 switches. But then in this case, with a multi-level converter, you have many, many switches, and your ripple frequency will increase, thus decreasing the size of all your passive components. And why do we want this? Because then that means that you have a physically smaller and lighter converter. Challenges. If you use a Flying-Capacitor multi-level converter, you will have control challenges. You will have to be able to properly turn on and off these switches at the right time. There's a lot of isolation concerns because your gate drive is now not referenced to ground. You also have some voltage and current ratings to deal with on your capacitors and other components. To operate this, to turn on the actual switches in the proper sequence to get your conversion result, you take your switches and you have some signals that are phase shifted by the number of levels, 360 degrees by the levels -1. So we'll go quickly over this, I think, just to get the general operation. So we make some assumptions. We have our input voltage here, and we have some capacitors at intermediate voltages. And this example is a 4-level converter here. So our first part of the switching cycle here, we turn on this switch 3A, and your voltage at the switch node is now 1/3 VN, as noted by this over here. Then in this second part of the cycle, none of the top switches are on. We have everything referenced to ground. This is yet another method of getting 1/3 VN. And we switch between these values. So that's during this time here. If we have a certain switching frequency for each phase, you actually end up with 3 times the switching frequency on the on the inductor switch node. And this is a factor of the number of, you can see over here, this phase shift is the number of levels minus 1 by 360. It turns out that your switching frequency will cause a ripple that is the number of levels minus 1 times the switching frequency that you use. And this is good because then that means that you can use a certain switching frequency and get, for free, the amount much higher at the inductor. And that drops the sizes of the inductors and the capacitors. So what does this actually give us? It means that we get a lightweight, high power density, flexible converter. So this is to go over some of our hardware design. We have our Flying-Capacitor multi-level converter on here. We've got some logic and power isolators. We've got our flying capacitors, as you can see in this schematic here. And we have a side view of, we can see what this converter actually looks like. And we can, as a lot of people have seen in the Palau group, we have some switching cells that we've designed to minimize the losses in the switching cells. We can see that over here there's a very, very small commutation loop, and that is to reduce the number of parasitics, the magnitude of the parasitic components that we have to deal with. So that is fine and dandy. We can go ahead and switch our converter using the conventional hard switched method, but maybe instead to drop our losses further, we can do something called zero voltage switching, and that is to turn on a switch where there are 0 volts across it. And doing that will drop the losses by quite a bit. So you can see that if we turn on the switches while VDS is 0, we can increase our frequency of switching, so that drops the passive component sizes even more. We can reduce the switching losses that you would normally get when you were switching a regular switch. And so challenges include that if you switch faster, you will deal with more. Your parasitics will now matter a lot. So that's all those parasitic inductances on here. Now they, because you're switching at hundreds to maybe a megahertz, hundreds of kilohertz to maybe a megahertz, you're now dealing with much more an effect there. And with the larger inductor ripple that is required to allow this to happen, then you maybe have more conduction losses. And the last challenge is that if you want to regulate the output voltage or output current, then you have to change the switching frequency, which may or may not be easy to do. So let's find out how this actually works. Here's a 0 voltage switching waveform, and you can see that this is for a conventional converter, which you can later extend to FCMLs. So in this state over here, we have an inductor current that is discharging this output capacitance of a MOSFET. So the MOSFETs will have some sort of output capacitance, and we just take advantage of this fact that this inductor current is going this direction and discharging both through this diode and through the output capacitance of the converter. In the second state over here, we turn on the bottom switch. So this is now regular operations. We have all of our inductor currents going through the load and through switch 2. The inductor current now ramps down during this period. And at the point of when the inductor current reaches close to 0, we turn off switch 2 again. And now the inductor current is negative during this period. You can see that it charges up the output capacitance of this MOSFET. And during this time, the voltage across this output capacitance is now increasing to the input voltage of the supply. And when we have the point at which the output capacitance is charged up to the input voltage, we turn on switch 1, again with 0 volts across the switch, which then repeats the cycle after we get back to the point. To talk a little bit about some of our results, we achieved this with a Flying-Capacitor multi-level converter. We were able to use about 500 kilohertz at maximum of our switching frequency, and that corresponds to about 3 megahertz at the inductor. And we got some pretty reasonable efficiency results. So this is using some naive control. We can see that at this point over here, we've done some 0 voltage switching operations, and it's this kind of an explanation of how we did that. So behind this point here, the converter is operating in ZVS regime. And this point in the middle over here is the point in which the converter is operating in partial ZVS, and that's saying that during the switch turns on before the capacitor charges to the proper voltage, and then that causes a bit of something we call hard switching. That's just turning on a switch in whatever normal method you would use. And over here we have the regular hard switching for efficiency. So in conclusion, our future work is we want to improve our efficiency by making this zero voltage switching automatic. We want to take this curve and just kind of extend it like that, using some sensors. Some acknowledgements, the APEC group for the little box. The Law Research Group, thanks for everybody for the help. And POETS is the power optimization of electrothermal systems, and I'll work with them. We have questions.
How flexible is flexible?
Flexible to the point of making about that much of a radius.
Okay. And is that related to your Young's modulus, or what is that? How do you quantify that?
So that is actually a physical constraint on this converter here. If you take a look at the side view, let's get over to the side view. So that side view over here. So at the point at which these capacitors touch is when you don't want to flex it much more.
That's right.
Are the switching cells up there also gallium-nitride substrate?
Yep.
What was the process like attaching the GaNs to the EGA packages?
Oh, attaching them?
Yes.
Very kind of long in the lab, making sure that the PCB wouldn't flex while I was soldering it down. But it was possible to get them down eventually.
So like we just soldered the GaNs on the campus.
Mm-hmm.
When you have the heat gun, like we had hot air sort of like blow from the bottom, does like that fluctuate? I mean, does that bend that much?
Yes, exactly.
So
So I had to adjust some parameters and then tape it down carefully and make sure it was actually solderable.
and my second question is, can you explain like how do you, I mean, future work, how do you change the frequency? Because definitely if you want to achieve ZDS across the full load range,
Mm-hmm.
as you said, you want to change the frequency.
Yep.
And how do you, is there like a control?
Yeah, so you would sense the output voltage and current, and then do some math inside your controller, which would then choose the proper switching frequency.
Do you have an idea for like fatigue? So like how long specifically your solder connections would be able to survive in a fatigue type situation?
So ideally, would actually not be flexing this actively. You'd flex it so that it conforms to the surface and then just kind of stays there. So this would be like, instead of making an FR4 rigid PCB and then trying to fit your enclosure around that, you would flex this to a certain amount, and then it would stay there for most of its operational cycle.
But in like a vibration type situation,
Mm-hmm.
Where there's your mean amplitude is
Right.
at a certain point, but then you have smaller vibrations on top.
Mm-hmm.
Is there any literature published? That's just something I'm interested in.
Yeah, I have not spent too much time on that at the moment, but I'd imagine that it would be, in a vibration environment, I think it would be slightly worse than a rigid PCB if you did not constrain it well. But if you constrain it well, it should not be too much different.
Cool, thank you.
Did you notice any change in performance when it was flexed versus not flexed?
Not appreciably yet.
All right, if there are no more questions, let's give our speaker another round of applause. And we'll take a quick minute to transition to our next speaker, so you can use this time to grab
Mm-hmm.
You are? Okay, good.
Hold on. I'm guessing this is it?
Yes.
Great. I love the puns, guys. Keep them coming. Am I good? Okay, this is good. So
Okay.
eraser slash try.
Thanks.
God, this mouse.
Is it the mouse pad or the mouse? Or no
There's
mouse
no
pad?
mouse pad.
Do you need to outfit yourself with the mic?
Where's that? Is the mic over here? Is that it? It's over here, Thomas. Tom, it's over here. Yeah. I don't know exactly what. Yeah, that's good.
All right.
All right. So we're about to have our next speaker present. And our next speaker is Thomas Foulkes. Thomas received his Bachelor's of Science in Electrical Engineering with a minor in Applied Mathematics from Rose-Hulman Institute of Technology in 2015. He is currently pursuing his Master of Science degree in Electrical Engineering at the University of Illinois at Urbana-Champaign. His research examines advanced cooling techniques, EMI filtering methods, and multi-level switch capacitor topologies in order to increase the power density of electric transportation inverters. Thanks, Thomas. Take it away.
Right, thank you, Matt, for that kind introduction. Today I'd like to share some results and observations from a collaborative effort to probe the cryogenic operation of gallium nitride transistors as well as other support electronics. Before starting, I want to highlight that this work was carried out in collaboration with newly minted PhD student or PhD Dr. Juan Colmenares from the KTH Royal Institute of Technology in Stockholm, Sweden. During our discussion today, I want to motivate why we should investigate cryogenic power electronics. I'll share some observations about the measurements that we took, and then hopefully send you away with the concept that GaN is a very appealing building block for cryogenic power systems. Probably a few of you immediately thought when I said cryogenic power electronics that we're going to send something to space. A few decades ago, NASA considered the power electronics to be one of the highest level system risks for the Pioneer and Voyager probes. Because of that, they actually packaged the DC-DC converters that connected the power energy system to all of the sensors and to the antennas right next to the radio isotropic thermoelectric generator, which is plutonium-238 oxide that actually generates the power for these deep space probes. And they did that because it keeps the board at a nice cozy 20 degrees Celsius, and they didn't want the power electronics to be the part of the system that would cause it to fail. So the power engineers said, I don't want to be the culprit when it fails, we'll have it be something else. So, but as NASA seeks to build more advanced probes for things like its asteroid retrieval mission, and also other probes to go to deep space, the question should be asked, perhaps if we examine the cryogenic operation, we could have more advanced systems, more advanced sensors for these devices. Another application a few of you may have thought of would be superconducting machines. So NASA has done on the aeronautics side a lot of studies that have highlighted, for example, for a Boeing 777 size aircraft which carries about 400 passengers, that they could use 10 megawatts of power generated by approximately 5 superconducting machines to power this aircraft in a distributed propulsion manner. But in order to obtain the best specific power density for this traction drive system, it would be of great value to actually package the power electronics right next to the superconducting machine, which of course will be cooled using a cryo-cooler. Thus, that begs the question, how well will power electronics survive in this environment? Now, a third application you probably didn't think about would be small aircraft. For example, drones or package delivery with quadcopters. And a Boeing Sugar study highlighted that liquefied natural gas is an appealing fuel source because of its high energy density. So again, this begs the question, how would power electronics survive in this application? Specifically, since the liquefied natural gas is given to us an operational temperature of about minus 161 degrees Celsius. However, for combustion, that temperature needs to be higher. Ergo, the power electronics, because of losses, could provide some of that heat to prepare the gas for combustion. Before continuing, to kind of give you a survey of the state of the art, both silicon and silicon carbide devices have been evaluated at cryogenic temperatures. While silicon does see some benefits in conduction and switching, as you decrease the temperature, it is noted that at specific temperatures based on doping, for example, a common one is minus 175 degrees Celsius, carrier freeze-out occurs where mobility no longer increases. Instead, you see dramatic degradation in the performance of the switch. Similarly, silicon carbide in these early generations of the devices, specifically for the IGBTs, have seen degraded performance at low temperatures. Gallium nitride, in contrast, has not been evaluated extensively at cryogenic temperatures, which was one of the main motivations for this collaborative effort. So, over the course of this experiment, we were evaluating, our device under test was an EPC 2034 enhancement mode gallium nitride switch. And we were using a lakeshore probe station, which allowed us to step the temperature in a controlled fashion from room temperature in 25-degree increments down to approximately minus 197 degrees Celsius. So we were using liquid nitrogen as our cooling agent. So I want to quickly share the 5 main kind of measurements that we took, kind of the rationale, why did we take these measurements. To begin with, we took 2 different kinds of static measurements. So the first measurement characterized on-state resistance as we decrease temperature. And this is important as the first indicator of what will happen to the conduction losses of the complete system, specifically the device, as we decrease temperature. Moreover, we examined the threshold voltage of the EPC 2034 device as we decrease temperature. And this serves as one initial indicator of the final switching losses that you could expect as you decrease temperature, because this will show us how the gate current, how quickly that charges and discharges the parasitic capacitance, and thus how quickly will the device turn on and off. We probe switching loss in an additional fashion with a dynamic measurement, specifically the industry standard double pulse test, which I'll discuss later on, which allows you to actually probe the switching transitions, both on and off, for the actual device. And we also looked at some support electronics. So this is important as we build to larger systems and also to drive the switch for the double pulse test. We examined a gate driver as well as a signal isolator. So when we were looking at the static measurement for the on-state resistance, you can see we attached a digital multimeter across the drain to source and biased the device so that it was on. And then we stepped the temperature down to cryogenic levels. And at every state, you can see initially, when we compare to the manufacturer data, we have strong significance. You can see a very nice trend down to cryogenic temperatures that corresponds to approximately an 85% reduction in on-state resistance, which is very exciting because this would correlate to a 5 times reduction in conduction losses. So for someone trying to design a high-efficiency system, these are great numbers to see. It's important to note that there is one other example of published research with gallium nitride in the literature. It relates to an earlier generation of an EPC 1010 device. In contrast, well, here you can see that as we decrease the temperature, we're not seeing evidence of carrier freeze-out above minus 200 degrees Celsius, which is very positive in terms of motivating this for cryogenic applications. Moreover, it's important to note, in contrast to the other work, our work, at every point we ensured that the device was at thermal steady state. The prior art dunked the device in liquid helium, so there was no comment in the experimental procedure from the prior art that said we let the device achieve thermal steady state before we took the measurement. So that's very important to note. Should you decide to evaluate a device, you want to make sure that the junction temperature is at thermal steady state. So when we examined the threshold voltage for the transistors, we decreased temperature. Again, we had strong significance when compared to the manufacturer data in the region that they test. But we did not see a major change in the threshold voltage. This 16% increase would not contribute, we believe, to major switching losses. So as this first level indicator, we predict that we will not see major switching loss changes. Pardon me. So when we examined the gate driver, specifically the TI-LM115, you can see that both at room temperature and at cryogenic operation, there's no anomalous turn on and turn off. The voltage remains unchanged. However, it was quite interesting to see that the delay time between the dark blue input signal and the output signal here, starting with the green dashed line being room temperature, going to this yellow line here, which is at the cryogenic temperature, you can see that this delay time decreases for both the turn on and turn off delay, and both are approximately symmetric, about 10 nanoseconds. So this will be important to keep in the back of your mind as we continue discussing, because this could contribute to perhaps how you might control a device at cryogenic temperatures if you want to consider this in terms of picking your dead times or your blanking times. In contrast, the signal isolators did not show any change in delay time between the room temperature and cryogenic results, even though it is also made on a silicon process. So now I'd like to share a little bit about the double pulse test. So the double pulse test, for those of you that don't know, is an industry standard technique to allow you to examine both the turn on and turn off performance of a device under test, which is placed in a half bridge configuration. The device that's placed in the upper portion of the half bridge will act as a freewheeling diode during a portion of the operation. So during the first pulse, the device under test is turned on, and we ramp up the current inside the inductor. And then in this pulse, we're able to examine the turn-off transition, and the upper device behaves as a freewheeling diode. And then during the second pulse, we turn off the freewheeling diode and thus examine the turn-on transient of the device under test. So for the test parameters of 50 volts and 10 amps, you can see from our experimental results that this agrees in strong significance with the theoretical parameters I just shared with you. So this should give you confidence that we implemented this test successfully. Of interest, when we look at the delay times as we go from room temperature to cryogenic temperatures, you see that there's that same 10 nanosecond delay. And we attribute this, as I told you to remember, not to the gallium nitride itself, but to the TI gate driver, since that 10 nanoseconds is curiously in line with what we observed for those measurements. Thus, we do not predict major switching transition changes as we go from room temperature to cryogenic performance for a gallium nitride transistor. In summary, we believe that gallium nitride is an appealing choice as a building block for cryogenic converter operations, mainly because we see a 85% reduction in on-state resistance, which will correlate to a 5 times reduction in the conduction losses. And we do not see major changing in the switching loss of the device, but it is important to know that the support electronics that you choose should be selected and characterized carefully such that you can account for this in your control schemes, should you care about the small change in the delay due to the increase in mobility of the silicon process. For future work, we're currently taking these building blocks and putting them inside larger converters and evaluating the converter's complete performance as we move to cryogenic temperatures, and we look forward to sharing that work with you all soon. I would like to close by thanking our funding sponsors, both the NASA Fixed-Wing Research Grant as well as the Power Optimization of Electrothermal Systems National Science Foundation Research Center. So with that, I accept your questions. Yes.
Typically measure, like, well, if I remember correctly, they typically measure, like, say, the energy per turn on or per turn off. Do you guys do this? Or what are you guys measuring?
We were actually just looking at the delay time. Yeah. So we were probing actually the transient performance.
Okay. Is there any plan, say, to measure the, like, say, like, per turn on, you lost, like, certain energy? I think that's, part of the double pulse test. You can test switching
Right.
loss by looking at the energy loss curve.
That's a good suggestion. There are a few additional things we're going to do when we evaluate other gallium nitride transistors, so that's a good suggestion. Yeah. Yes.
How do you test the threshold voltage of the gate?
Oh, so we were actually measuring the gate to source voltage of the device as we went to cryogenic temperatures.
But threshold voltage is kind of unclear because
So we had a defined current through the device based on advice from the manufacturer was 7 milliamps. So that was kept constant. Does that answer your question? Okay.
When it's over 70 milliamp, it define that as a...
Yes. Yeah. But again, that was provided by the manufacturer. There are some questions where that number arrived from. 7 is a unique number. It's prime. But 7 was suggested, so that's what we used. Yeah.
I know that in the experiment, you kind of just ramp the temperature down slowly, but are you going to do any thermal shock test? I mean, would it be in a position where it would go from like room temperature to liquid nitrogen in a few seconds?
We had not discussed doing thermal shock tests, but perhaps as we do work with a complete converter, that could be of value to know if it's the building block that breaks because of thermal stress or if it's something else that breaks because of thermal stress. So that's a very good suggestion. We'll take that into account. We had not proposed that yet. Yeah. Yes?
Would it be possible to operate the GaN in a cryogenic condition if you're not under a vacuum atmosphere?
Pardon?
So you did these tests under vacuum, right?
Right, to prevent condensation, yeah.
Would it be possible to do it without a vacuum?
Yes. Yeah. So we're actually using a cold plate right now for the complete system, and it's kind of embedded inside of a thermal compound. Yeah. So if you packaged it, yeah, that would not be a problem. Yeah. Dr. Milkovich, and to give him a plug, is our collaborator from the mechanical heat transfer side, and he is the king of conformal coats and unique superhydrophobic and superhydrophilic materials. So if you would like to partner with someone who has expertise in those materials, he has very unique recipes for making these things and probably could find one that would be right up your alley, what you need. So. All right, thank you.
If there are no more questions, let's give her. In terms of announcements, I only have one. That is that if you want to submit a digest technique,